Hello, and welcome to chapter 18, right? So if we just did chapter 17, that was nucleophiles adding to polar pi bonds, right? So something with a negative charge coming in and reacting with a functional group like a ketone here. Today we're going to look at how can you do reactions with weak nucleophiles. So this is really what chapter 18 is all about. So if you have a reaction with a ketone or an aldehyde with something that's not such a good nucleophile, right? So a nucleophile is something that has a lone pair of electrons that can donate, usually something that's partial negative, like a weaker nucleophile, or full-on negative charge, being a stronger nucleophile. This would be a weak one, right? So this reaction to form this new functional group is slow, right? Not a very reactive nucleophile, not a very reactive electrophile with the ketone either, so it goes slow, like really slow, but eventually you can make this new functional group called the hemiacetal, right? So if you look here, clearly this group here came from the alcohol, right? Where did the hydrogen go? Well, that's part of the mechanism, right? So to make these reactions work, what you need to do is add an acid or a base to get things started. So that's essentially sort of two different versions of ways to do these same reactions to make this same product, as just whether or not you use an acid or a base to start. So two different mechanisms depending. If you remember our previous chapters, we looked at things like, all right, well, alcohols are not very reactive. Maybe you need to make it a better leaving group, or you need something to sort of activate and get reactions going. This is the same sort of concept. So whether we add acid to make our reactions start faster, or base, that'll change the way the mechanism works. So let's look at one of those mechanisms. Right, reactions to make either hemiacetal or an acetal. We'll do the hemi because that's a little bit shorter. So let's start with the base catalyzed. And kind of walk through that as we go. Right, so what happens really is the strong base, and let's just use generic base at this point, will react with that alcohol in the first place, right? So if we're trying to do this reaction, oh, forgive me, I gotta draw out my bond here. If I'm gonna do this reaction, I need a stronger base to basically activate my nucleophile. Right, so that base will take this hydrogen, break the electrons toward the oxygen. That's going to give us a strong nucleophile. And then it can basically go ahead and react like we've seen before, right? So now I have something with a negative charge, and so if I do the mechanism that I'd shown you previously and is on the notes page, all right, let's do that now. Right, then it's going to react the same. So now I've used my base, so now this is a strong enough nucleophile to just do the typical addition. I'm just drawing it up here to kind of be a little more consistent, right? So this is starting to look like the hemiacetal now, right? So on the same carbon, I have an alcohol group and an OR, like an ester, but if those are bonded in the same spot, they get their own functional group name as hemiacetal. These kind of things show up in carbohydrate reactions a lot, right? So sorry, back to the mechanism though. Right, so we're almost done, right? There's not really that much left. So in order to make this neutral and back to the OH group that we would kind of expect in the end, then we need to do a proton transfer from the solvent or from the reactants to make it go. Right, so we probably have some more ethanol around. I have my OH group and my other, right, so really could zoom out on there a little bit, would be nice. now we have the hemiacetal functional group. So sorry about moving the paper around a little bit. I need to make sure I have enough space next time. Right, so this is the base catalyzed view. Essentially, it's going to react exactly the same as we've seen before, except there's an extra step where that base comes in here and activates my nucleophile. So now it's reactive enough to basically do the same mechanism from chapter 17. The base catalyzed version to form a hemiacetal is not too bad. So next video we'll do the acid catalyzed version.